Good evening, guys. Um, Hope all of you had a restful weekend and just keep powering through. We have 3 days until Thanksgiving break, so just keep powering through. So for today's sort of case study, I was inspired by a discussion that a friend of mine and I had surrounding the impacts of COVID-19 on San Francisco. And one of the aspects that came up was that of crime, how would crime have been affected? And at that point, neither of us could do anything but speculate. So therefore, I thought that would be an interesting question to sort of look into how crime has been affected in San Francisco due to COVID-19 and what sort of impact it's had. And today I'm going to be taking you through the whole sort of data process, right from acquiring the data to cleaning it and to finally visualizing it and deriving insights. So firstly, to get crime data, uh, there's a very useful website called datasf.org. And uh, you have a lot of government data sets available. So firstly, I'm probably going to go to public safety, and now I'm going to go to the police department incident reports from 2018 to present, since we want information on 2020. Right. Let's view the data. And now what you're going to notice is that we have data right from 2018 all the way to 2020. So we would want to apply a filter on our data to ensure that, so we add a new filter condition here to ensure that the year is only 2020, because then the file is just going to be humongous to download. So let's say we want the incident year to be 2020, and we would add this filter condition. And finally, then the table has now been filtered only for incidents with 2020 as the year. Now we can just go on to download it just by saying export and saying CSV. So now you can have a CSV file which downloads. I won't download it here. I've already done it. So once you've downloaded your CSV file, you'd want to upload it onto the same directory as your notebook. So for me, I have my notebook here, which is SF crime data main. And I also have my CSV file here, which I've renamed to sf1pd.csv. So yeah, we can begin. So firstly, of course, I'm going to import pandas pd, standard stuff. Now I'm going to read in this data frame using our pandas command, pd or vcsv. So it's going to take a bit of time because it's a large file. Next, just to make sure that we're dealing with 2020, I'm just going to filter the incident year to 2020. And right off the bat, I noticed that this particular date time is in an interesting format. So if I want to answer a basic question, which is, how did crime sort of change in San Francisco? I would likely want the month, right? And as we can notice, the month is sort of hidden here amongst sort of the year as well as the day and the time. So we'd want to be able to extract the month. So in order to do that, so this is our data frame that we're going to be working with. It's a pretty big data frame with about 2,900 rows and 26 columns. So I'm going to define a splitter function firstly, where I essentially split by the slash in order to just take sort of the month and extract the month. So I define the splitter function by sort of as the command you can see here using the following method. Now I'm going to sort of use the map function to be able to map this splitter function onto my column. And in this case, my column is this incident date. So I want to extract just the, oops, my bad. So I run this in splitter and yep. And finally, I just want to make sure that the month that we extract is an integer. So I'm using .astype int to be able to convert it into an integer. Just keep in mind that sometimes you might get these red warnings, but as long as your code is running fine, you shouldn't sort of worry about it too much. Now I'm going to plot a histogram to see the distribution of crime across the months. And it is interesting to note how from January, that is the first month, there was a gradual fall in the level of crime, or by the time we reached April. I think one hypothesis is that the lockdown had an effect on decreasing the crime levels. Now, say we want to, uh, have this whole visualization as a line plot. We can group by the months and aggregate on the count, so we can have a sort of more clearer understanding of it, because you can't really see the trend line with uh, a histogram. So assuming we want to see the trend in a sort of easy to read manner, we can have a simple line plot, and we see how crime has fallen by a significant amount, after the lockdown was implemented. And then it's risen a bit, but it's been generally below the January or the pre-COVID levels. Next, we're going to do three things. Firstly, we're going to break down crime by neighborhood. Then we're going to break it down by incident type. And finally, we're going to break it down by the time of occurrence to see what times crime is most frequently sort of occurring. So firstly, let's start with the neighborhood. I am doing the same thing. I'm grouping it by the police district, and I am aggregating over the count. And let's see what this gives us. SF crime name. Let's see what this gives us. So this just gives us essentially the count of crimes occurring in different police districts. So now a challenge from here is to ensure that we get back police district, which has been made an index. So when you group by the police district, it becomes an index. So now we want to get it back from an index into our data frame again, so that we can make some sort of plot out of it, potentially a bar plot. So the following command here, where I have selected all the rows and just the zeroth column, which is the police district index, and I have said toFrame.reset index, and I've stored that in the name variable, which is now our new data frame. So using the following command, I have now moved back police district from an index back to our data frame, and we get the following sort of table. And finally, we can use the plot.bar sort of function using x equal to police district and y equal to incident date time, since that simply just has the counts, right? So we can do the following and get some sort of a distribution on where the most frequently, which sort of police districts have the most crime. From this, we can see that the northern police district has the most crime, and I guess out of SF, since it's not in the city, likely has lesser crime. So I'm not too familiar with San Francisco, but so I can't sort of give any insightful comment on this, but this seems to be the general trend. For those of you who are from San Francisco, I'm sure you could read into this. Next, we might want to break down crime by the incident type to know, what kinds of crime are most frequently occurring given COVID-19. So again, let's just read our main data frame, which is SF crime 2020. And now we group by the incident description and we aggregate on the count. So since we are trying to sort of get more information on the incident description, we can do the same and see that similar to before, we get a data frame with just counts, and the incident description is now in our index. So same as before, we would want to get incident description out of the index and back into the data frame so that we can make some sort of reasonable plot. Okay, so let's just explore this incident description column, and we see that there are about 40,000 incident descriptions. So it's not reasonable to have a visualization with 40,000 different types of incident descriptions. So maybe we let's just sort of shorten it down and take the 10 most frequently occurring kinds of incidents. So we can do that by saying A, which is the previous data frame, A dot sort values, and we're sorting it by the incident date time, which essentially is our count now. And we're doing in descending order, and by saying ascending equal to false. And after that, we're just using the iloc command to select the top 10 rows and all of the columns. And same as before, we are now resetting the index to obtain a new data frame with just the incident description and the incident count, essentially. And again, same as before, we can just use a bar plot to see that theft from locked vehicles seems to be the most frequently occurring, and that too by a significant margin. One hypothesis that I can think of might be that since most people are quarantining at home, people have left their cars on the street. And as a result, it's easier now for burglars or for robbers to sort of break into cars and break into the windows and steal stuff, just off the top of my head. And yeah, that's definitely pretty interesting. And finally, the last question I'd like to think about is what time of the day does crime occur the most? Off the top of my head, my initial hypothesis might be that, maybe crime occurs the most during the night, since that seems like sort of most conducive for crime to occur. So let's see. So similar to before, we're going to have a splitter function, but this time we're calling it splitter time. And here now, instead of splitting by the slash, we want to split by this colon here. Since we want to obtain just the hours, we want to obtain the hours of the day. So yeah, essentially we are taking in a column and we are splitting it, splitting each entry of the column by the colon and extracting the 0th element, which in this case would give us the R. So let's define that, splitter time. And now I'm creating a new column called SF crime 20, called R in our data frame. And I'm again mapping the function that we just created, the splitter time function, onto our incident time column. So onto this particular column here, onto the incident time column, I am mapping this function splitter time. So what mapping does is that it takes a particular column and a map applies the function that you've inputted and applies the function onto the whole column. For those of you who've taken data 8, it's pretty similar to the dot apply function there. So let's do that. Let's map it onto the whole column. And now we're going to again do the same thing and just ensure that the R's that we've extracted are in fact integers, and let's just sort it by R's of the day. So let's sort in ascending order so that we have some sort of regularity. And now we can finally plot a histogram to see when crime occurs the most. And it is actually surprising in that it seems that the bulk of crime seems to occur during the day between, I'd say, 11 a.m. to about 5 p.m., with the most frequently occurring time being 3 in the afternoon, which is extremely surprising. I'd have expected it to be during the night, the most frequently occurring time, but I guess that crime seems to be occurring more frequently during the day now. And I'm not really sure why. I guess more research will need to be done to sort of delve into that question, but I would only suppose that would probably be because of people being quarantined in their houses. So, it's more conducive to engage in crime during the day. But then again, this just shows how, having data allows you to really test out your hypotheses that you have. And, in case the data doesn't support it, you can actually say with certainty that your hypothesis was wrong and the data indicates otherwise. With that, we come to the end of today's presentation. I hope you guys sort of had some fun learning about, usual or unusual trends in San Francisco crime. I'm sure I sure had a lot of fun sort of creating this presentation and really, exploring this data. But yeah, I hope all of you have a great day, and see you guys soon, and stay safe. Talk to you guys later. Bye.
Hello. My name is Siddhant, and today we will be doing a case study on Spotify data. So I was supposed to do this lecture with Saeed, but unfortunately he's not feeling very well, so I will do both parts of it by myself. And today's topic is basically an explanatory data analysis, that is an EDA, on Spotify data, which contains the data of artists and songs and the details about each song. And this will primarily include data visualizations as well as a bit more advanced hypothesis testing than the one you may be familiar with from lecture. So let's get started. Let us import the libraries. NumPy, Pandas, Matplotlib, and Seaborn is another library that we can use for visualizing data. We read a data frame, and there we go. So this is the data frame we're working with. Here we can see that we have the artists, and we have the song names all the way here. And we also have a bunch of information about the songs, such as acousticness, the danceability. I don't know how to calculate that, but we have the danceability. We have the ID, and we have a bunch of other information about the song. We can also find out more details about the songs, or the dataset, I'm sorry, so by calling it df.shape. It tells us that there are almost 170,000 entries, which is a lot, and 19 columns, which are all these over here. We can also explore and see if there are any null values that we want to deal with. Luckily for us, there aren't any, because this is a dataset that was already cleaned by someone and they uploaded it to Kaggle. If you want to have more experience or go through an example that involves cleaning of data, I'm sure that one of the other lectures today would be going through that. So the next thing we want to do is we want to drop columns that we don't think are particularly relevant for our analysis. So over here we have the ID, which seems random. Explicit content, our focus would probably not be on explicit content. We have the mode, and we have a release date, as well as a key. So we don't think that that would be important. And over here, we can see that all the columns have been removed. Okay, great. So the first thing that we might want to do is explore how all these columns sort of affect each other. And luckily for us, Pandas has a handy function to do that, which is called correlation, or CORR over here. So basically what this does is that it computes the correlation coefficient between each pair of two columns. So over here, we have the correlation between acousticness and acousticness, which is 1. So note that the correlation of every column with itself is 1. So all the diagonal values in this data frame, are 1. And we also notice that the correlation with acousticness with danceability is minus 0.26, which is slightly negative, but not too much. And we also notice that something like acousticness and energy are pretty strongly negatively correlated, so it's minus 0.75. So this seems interesting, and this is actually something that we can explore later. And like looking through the rest of the correlations, we see that this is a similar value. It is actually the same value. It's energy and acousticness. The correlation is the same both ways. And I feel like this is the strongest correlation we have. We have valence and danceability also go quite well together, which makes sense because valence is the happiness of the song. Happy songs are mostly danceable, I feel, hopefully. Sad songs aren't quite danceable. So the next thing we want to do is plot this beauty. So here we have a particular visualization of this correlation table. And this is done by the Seaborn library. And this is called a heat map. It is essentially it tells us the same thing as the correlation table, but it looks much nicer. Plus it has color code, so we can look at it and we can intuitively make out which columns are strongly correlated and which columns aren't. So over here you can see that energy has minus 0.75, which is kind of dark green, which is quite negatively correlated. And we also have a bunch of darker blue ones, and the light blue ones are pretty strongly correlated. So this is again valence and danceability. So just as a disclaimer, don't worry too much about the code. Most of these functions you can look up online. You can consult the documentation. I mean, I pretty much didn't know half of the syntax for all of these, so that's not a worry. As long as you know what you want to be doing, you can just use Google, Stack Overflow. Those are some of your most important tools. So after you do that, we can move on to seeing a few values. So notice that we said that energy and acousticness appear to be quite negatively correlated. Well, let's look more into that. So here we use a group by function to check for each artist what is their average acousticness and energy. So over here, that's why we use the mean, because we want an average of acousticness and energy. And we want to see which ones have the most acousticness. So over here, we see that we seem to have quite a few instrumental ones, I believe. So there's a piano over there. So I believe that's quite instrumental. And that can lead us. And the more interesting observation over here is I notice the energy values are generally quite low, which can lead us to conclude that, okay, artists with high acousticness values usually produce low energy tracks. And this is something that we can actually test. So quite soon into our EDA, we have a testable hypothesis. That is exactly what we're going to test later. So another thing that we might want to do during the EDA is see how all these columns change over time. So let us do another group by. This time we want to group by the year, and we want to have all these various details of the songs, and we want to see how they change each year. So let's say in the year 1921, the danceability is 0.425. In the year 2020, it's 0.673. So we get an idea that the danceability of songs have generally increased. Although not too much, because if you look at over here, it's 1925, it's 0.57, and 2016, it's almost 0.6. So it hasn't increased by too much, which was interesting. And we can do a similar thing for all the values, but instead of going through it in these abstract forms, we can plot graphs. This is using Seaborn again. So Seaborn generally tends to be a bit cleaner than Matplotlib. That's why we prefer it. And over here, you can see a bunch of interesting things. So you can see that acousticness starts off at a pretty high value, but the general acousticness goes down as the years go on. And similarly, if you look at energy, which was the yellow line, it sort of starts off very low and it just keeps on increasing, and it is quite high at 2020. While the other three values pretty much maintain a similar sort of level. But this is really interesting. It ties into the relationship between acousticness and energy that we're talking about, which is exciting. We are getting more data. And over here, we can then see some. Okay, so over here, we can move on to the popularity of the song. So let's say, well, we all know which songs are popular right now. I mean, we want to be cool, right? So over here, you can see that The Weeknd, Blinding Lights, yeah, pretty obvious. That's pretty popular right now, as well as Roxa, The Baby, and That Red. So these are a few songs that are popular. Over here, we use the sort values function of the pandas data frame, and we want to sort it according to popularity, and we want a decreasing of it because we want to know the most popular songs. So we look at this and we see that these are quite popular. Also notice that there are a few popular songs over here. So Louis Fonsi is quite a popular artist, but the thing with Spotify is there are usually multiple versions of a song. So, I mean, perhaps not a lot of people clicked on this one. So let's look at Blinding Lights, because that is apparently the most popular song, and we are quite generic. So over here, we see that there are, again, two entries for Blinding Lights because Spotify is weird that way. Apparently, it's because the artist can release one as a single and one in an album, but that was a good thing to know. And let's see if you want to figure out how many artists there were, unique artists there were in the dataset. We know that there are more than 33,000, which is quite insane. Now let's say we want to look just at 2020, and we can filter the year, just be 2020, and store it in another data frame, which has songs only from the year 2020. And we can find a number of unique artists in 2020. That's just 1,000. And we can find the most popular artists. So over here, we find a value counts, which just tabulates the number of occurrences of that particular artist in the data frame, which basically measures how many songs they put out in 2020. And we see that Lil Uzi has quite a lot of songs. The Weeknd also has quite a few. Lil Baby has a few. And yeah, and these artists are generally the ones that you see headlining throughout the year. That's why they have so many songs. And we can store this in a list. So this is pretty much the exact same code as this. We just want the indices out of the artist names. And over here, we can, so this basically stores it in a data frame which has the artist's name. Let's see if I can pull it up. Okay. So which has the artist's name for each year. So we see that Dua Lipa in the year 2015 had just one song. And like in 2019, she also had just one song, but in 2020, she had 15. And we have a similar thing for all the artists that we saw over there. And oops, that is petition. And over here, we can see that this is a sort of visualization of what we essentially got over here. So we know that, let's say, Future in 2020 has 15 songs. And over here, if you look at Future, which is the orange line, it is over here. Oops, it's over here. It is over. No. Yeah, it's somewhere over. No. Okay, that was sample 15. It's over here. That's 15. So we know that this is pretty much plotting out how many songs each artist released every year, but this looks kind of messy. So what we really want is an alternative to this, if we can. And in order to do that, we are introducing a new library, which is kind of awesome. So in order to use the library, which is called Plotly, we have to get a data frame in order first. So essentially what this code does over here, what these blocks of code do, is to create a new data frame, and then it sort of tabulates this sort of number of songs that it has per year. It's essentially doing what this data frame does, but in a slightly different way so that our other function can use it. I don't worry about that too much. This is sort of extra, but it is really useful. I'd recommend you go slowly through this code and just look at the documentation and see if you understand it. Or you can contact one of the DAs. We'll be glad to help you out. But over here, we can see that this is an interactive plot. It's an interactive bar chart, and it goes from the year 2012 to 2020. And it has all of our artists in different colors, and they have different columns as well. And if I play it, oops, let's all play. You can see that as the year increases, we sort of like update the count. And this over here is a cumulative sum. So these are the combined totals of all the artists, of the number of songs that each artist has. So over here we can see that Lil Uzi and The Weeknd appear to be the most prolific, followed by Youngboy. Love and Dua Lipa don't seem to have too many songs out, but they're still pretty popular. So yeah, and that sort of concludes the visualization part. So again, do not worry too much about the code. This is quite abstract, and we haven't really introduced this. But if you are curious about how Plotly works, I highly recommend you check out the documentation. There are a lot of good tutorials out there, which will help you go through it and create cool visualizations. I will see you later in the hypothesis testing. Bye. Hey again, so welcome to the second part of this case study, which we test out our hypothesis between energy and acousticness. So just going back to our plot, we can see that as time increases, acousticness, that is the red line, decreases by quite a lot, while energy, the yellow line, increases by a lot as well. So this may imply that there may be some sort of correlation between the two factors or the two characteristics of songs. And let's try that out. That sounds like a testable hypothesis. This is actually where hypothesis testing really comes in use. So over here, the first thing we want to do is that we might want to create a data frame with just these two values, since these two are the only things we want to test. So I defined a new data frame called hypedf for hypothesis testing data frame. I was too lazy to write those out. And we can see that it only contains the energy and acousticness, but it still contains all the rows of our original data frame. So it has all the entries. And over here, I am calculating the correlation using a module from SciPy. And we can see that it's pretty negative. It's minus 0.75. So if you go back to the correlation map over here, you can see that the correlation between energy and acousticness is minus 0.75. So this is basically just telling us the same thing. And now when we get back, we know that, okay, so we have this pretty negative correlation between energy and acousticness. What does that mean? Is it some sort of like causal relationship? Do songs that have high energy inherently have low acousticness? Is that a thing? Or maybe there's some sort of confounding variable that affects both of them. We don't know. How do we find out? A hypothesis test. So basically what we want to do is that we want to find out if this correlation is statistically significant. Or that is basically if we can discard the possibility that it is just a random freak occurrence. And over here, we define a couple of hypotheses. So this is very similar to what you've done in your assignment. The null hypothesis is that the energy and acousticness are independent of each other. So they should not influence each other in any meaningful way. And the alternate hypothesis is that there is an inverse dependence between energy and acousticness. That is, songs with high energy tend to have low acousticness and vice versa. So the first thing that we might want to do is we might want to split songs into high and low energy. And the way that I've defined them over here is that high energy songs are one standard deviation above the mean energy, and low energy songs are less than one standard deviation below the mean frequency. The mean energy. And the choice of energy was completely arbitrary over here. I could have picked acousticness. This was very arbitrary. So over here, I just calculated the mean and the standard deviation of both the energy and acousticness, because we might need that later. And over here, I have defined low energy songs to be all the songs in HypeDF that have an energy less than the mean energy minus one standard deviation. And similarly, the high energy is all songs of HypeDF that have energy greater than or equal to the mean energy plus one standard deviation. And we see that we get nearly identical sizes. So both of them are around 68,000 songs, which is always nice. And let's say the mean energy of the low energy, over here. So we want the acousticness. So the mean value of acousticness for low energy songs is 0.88, and the mean value of acousticness for high energy songs is almost 0.13. So again, it kind of seems that it might be related in some way, right? But we can't just say that. We need to actually go through the entirety of the hypothesis test to say that. And let's say we want to plot this. We can pull up a line plot, which basically takes energy on the x-axis and acousticness on y-axis, and we gather data from the hypothesis data frame. Again, over here, I'm using the Seaborn library. It is very convenient when it is not taking ages like now, because it essentially makes visualizations a lot cleaner, and we don't have to worry about axes or figures, usually if you just want to make quick plots like this. Well, in Matplotlib, sometimes you need to do that. This is taking ages. So until then, let me just go over a quick summary of what we want to do. So what we want to do is that we want to simulate under the assumption that our null hypothesis is true, right? Because that is how we conduct hypothesis tests. So if our null hypothesis is true, that means that songs, the energy and the acousticness of songs, there is no correlation. So a song with high energy could have either low acousticness or high acousticness or somewhere in between. It doesn't really matter. So we should get an even distribution of acousticness values if we randomly sample songs from high energy. And this basically implies that the difference between these sample means and the mean acousticness should be quite small. So it doesn't matter if we have high energy songs or low energy songs, we should get pretty much the same distribution of acousticness. And over here, I'll get into why we choose to simulate 200 samples. But what this assumption basically lets us do is that we don't have to simulate under the null hypothesis because, oh, the plot is back. I will get back to that later. So over here in the line plot, you can see that we have a lot of songs that have sort of zero energy and zero acousticness. So I'm assuming these are songs that people don't really listen to that much. And we also have quite a few that have very high energy and a variable value of acousticness, which is concerning. We will address that in a bit. But mostly we can see that there appears to be a negative linear relationship between these two variables, which is interesting, which sort of conforms to what we know already. And nope, I do not want to run that again. It's basically the same thing. And over here, if I want to see the acousticness, then I see a similar thing to what we saw before. That is, there's a lot of songs that have energy values of 0 and have a ton of acousticness. So this is where there's a problem, right? Because, okay, I probably needed the previous one. Let's save this one pretty quick. But if you remember the previous slide, remember the previous plot, then you know that there are a lot of songs centered around the 0 acousticness mark, and similarly for the 1 acoustic mark. So this is not really a Gaussian distribution, right? This is a bimodal distribution, and this is sort of hard to work with generally. So what you might want to do is convert this into a Gaussian distribution. Because if you look at the other variable that we are concerned with, I cannot spell today, energy, yeah, probably have to call this first. Then we can see that this is a fairly Gaussian distribution. So it has a fairly normal shape. So it's a fairly normal bell curve, but acousticness does not behave quite as nicely. So what we might want to do is use a statistical technique called sampling distributions of sample means. It is long, but essentially what we're trying to do is that we want to sample items from this particular data set, from this HypeDF data set, and you want to take the mean of those samples. So since we have an equal, not an equal, but like a higher probability of taking both a higher and a lower value in the same sample, because this data is quite bimodal, they will sort of cancel out, and we'll get a value that's kind of in the middle. So if I take 3 samples, I might get 0.0, I might get 1.0, I might get like 0.4, which will give me a mean of, again, about 0.45, which would be in the middle. So this is actually a trick that helps us get a Gaussian distribution or a normal distribution. And if I run this, it's going to take a while, but we can see that it will be a fairly Gaussian distribution, just like that, fairly normal distribution, which is quite beautiful. So again, this is a statistical concept. I use it over here so that it makes this assumption possible. It makes that the even distribution of acoustic notes values that only applies when we have 200 samples at a time, because this is what we tested for. So when we sample 200 songs at a time, we get this standard distribution. So we want to continue with that. And over here, I've imported a data science class because that has a few important modules. And I've defined a particular test statistic. So this is actually a special test statistic. It's called a z-score, which is the number of standard deviations between a measurement and a mean. So it's basically how far a measurement is from the mean. So over here we can, so a z-score of 0.5 would mean that a measurement is 0.5 standard deviations above the mean, while minus 1.5 would mean that the measurement is minus 1.5 standard deviations below the mean. Great. So now what we want to do is our assumption for null hypothesis. So this is the clever part. So instead of simulating all the values under simulation, which would be kind of difficult in this case because you don't really know what our proportions are, we are taking a bit of a shortcut because we know that this would give us a normal distribution, right? And we already know that energy has a fairly normal distribution. So we can just assume that the sampling would give us the same sort of distribution. So let us, this should be called out, that's my bad. So over here, we can see that this is basically just defining a normal distribution and centered around the mean of acousticness and the mean standard deviation. So this is just, it's sort of a trick, it's sort of a hack that gets us, and this is not truly rigorous. To be rigorous, we should think of a way to run simulations with a null hypothesis too and check if it's a normal distribution, but I'm going to skip this part because, yeah, it's pretty time consuming. And now we can move on to actually taking samples from the hypothesis from the low energy data frame. Let's take it from low energy data frame first and see if this conforms to what we see. So let's say that, why do I have 200? Let's say we want 200 samples at the start. And we want to take just one sample. So one sample from the low energy data frame has a mean acousticness of 1.09, which would be somewhere over here, which is kind of high. It's 1 standard deviation away from the mean, because that's what our measure tells us, our z-score tells us. And we want to do this for a bunch of samples. We don't want to do it for just one sample. We want to do it for, over here, I put down 10,000. That seems like a good number. And we're basically doing the same thing that we did over here. I'll write this one. Should have played some music. Should have got some music. Oh, there we go. So over here, you can see that there is a bunch of different means over here, but they are pretty close together. So we have it from the range of, it seems, 0.95 all the way to 1.08. So they're pretty close. And if you take the mean of all these values, then we get 1.027, which we can take as our test statistic. And if you were to plot this test statistic on this graph, we'd see that it sort of lies at the 1.0 mark. So it's one standard deviation above the mean. Now, what does this mean? We need to somehow convert this test statistic value to a p-value that basically tells us whether our result is statistically significant or not. And now here's the beauty of this, right? So we picked a certain special value called a z-score, right? So the thing is that so this special value, the z-score, actually allows us to go really quickly to a p-value. So this is kind of the motivation behind using the z-score, is that we have a function, specifically the cumulative distribution function, that converts the z-score to a p-value really quickly. And over here, I can see that the particular p-value is 0.847. That means that 0.847 of all values lay to the left of this point. So what we actually want is whatever lays to the right of this point. So that's why we want to do 1 minus this. And we get 0.15. So we notice that there's only 0.15 or 15% of values that can be graded in this. However, if we are assuming a significance level of 0.05, this is not enough to suggest that the acousticness depends on the energy, because we want to have something lesser than 0.05. And although they are correlated, we cannot conclude any causal dependence because we fail to reject the null hypothesis, because there may still be, I mean, there's a 15% chance that we can get this just by a random roll of dice or like a random luck. And if you were to repeat this really quickly with high energy instead of low, so if I put in high energy over here, I really can't spell it today. Energy over here, run this, you get a negative value, which makes sense because we'd expect low acousticness from high energy. Over here, we found high energy, run this, that'll take some time. And over here, since we'll have quite a low value, we'd want everything to the left. So we get rid of 1 minus. That's 1. Great. So over here, again, we see a bunch of values that are fairly clustered together. So it's from minus 0.95 all the way to minus 1.07. And the mean is minus 0.97. If we compute the test statistic and plot on this graph, we see that it's quite to the left. And over here, we can see that statistic. So over here, we just want whatever's to the left. I believe that this plot is a bit weird. But basically what we want is everything to the left of this, so that it should be extending more towards that. And we get that there are 16% of the values that we can randomly generate would be towards the left. And again, this is not enough evidence to suggest dependence. So as a general rule, although there is significant negative correlation between these two values, there is not enough evidence to conclude that we have a causal relationship. So this is a fairly important use of hypothesis testing. I hope you found this useful. I'm sorry it was a bit long, but yeah, hopefully you found this whole case study useful. Bye.